most solid learning occurs when I discover something by myself. What I discover by myself, I will not forget. Especially in math, there are many things I can discover by myself. In history, in geography, and in many other subjects, I depend on information by other people. For example, if I want to know where Bolivia is, or when George Washington was born, I have to find this data in a book, or a teacher or someone else has to tell me. There is no way how I could deduct these things by myself. But mathematics is completely logical. When I understand its fundamental principles, I can from there construct the whole of mathematics by myself. By doing this, I develop my capacity of mathematical thinking, and I will no longer need to memorize a huge amount of formulas and procedures, because mathematical thinking enables me to discover the formulas by myself. Let's take an example from elementary education. Once I understand what a multiplication is, I can construct the whole multiplication table by myself. I do not need anybody to teach me that 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, and so on. I can discover these numbers by myself. So, if we want children to learn math by their own investigation, we will not give them a cookbook. We will not give them a multiplication table and say, memorize this. Instead, we will help them to understand the principles of what a multiplication is. For example, we can explain to them that the multiplication is many of the same thing. I have multiplied this paper shape by 5. Or we can draw a rectangle and explain them that the number of squares it contains is the multiplication of its sides. So the child can discover by his or her own activity the results of the different multiplications and can build his own multiplication table. We can give them some additional challenges for investigation. What happens when we multiply a number by 1? And what happens when we multiply a number by 0? How can we multiply large numbers? For example, 3 times 21 or 3 times 342. At that point, it is not necessary that the child discovers already a generalized procedure for multiplying large numbers, not speaking of the standard procedure used in schools. That will come later. Maybe a child suggests that we can add 342 plus 342 plus 342, and that is equally valid. The important thing is that the child processes mentally the concept of multiplication and that he reflects about that concept. And at that point, it is not even necessary that this concept is completely correct and professional. Actually, a professional mathematician will have a different concept of multiplication, one which even many teachers do not really understand. But with children, we do not need to go into this. It is sufficient that they have a concept they can understand and which enables them to go on reasoning from there on. So what we are doing is empowering children to do mathematics by themselves, so they do not depend on other people's instructions. Math is not something some teachers invented arbitrarily. Math is based on a higher logic, on universal principles. So we want the child to submit to this higher logic, not to the arbitrary instructions of a teacher. This higher logic is the same for the teacher as for the child. So we want that the child comes to the point of realizing, I can do this by myself. We also want to keep the natural curiosity of the child intact. Every little child has a natural desire to know, to investigate, and to experiment. But when we give them all the answers in advance, we will kill their curiosity. Instead, we want to direct their curiosity towards math and give children the opportunity of discovering answers by themselves. This works only if we give children lots of time. Mathematician Keith Devlin from Stanford University said, "We professional mathematicians despair at school systems that impose tight time limits on completing mathematics tests and encourage fast working. Real math takes time." Actually, quick answers are mostly superficial answers. When we require quick answers, we promote superficial thinking. We should give children sufficient time for thinking. We will also have to help children to persevere and to overcome frustration. When you do a mathematical investigation, there are moments when you just don't see anything, no solution, nothing which leads you further. But don't give up. Maybe you can do something different, something you did not try before. Or maybe you have to leave the problem until the next day. And maybe suddenly you get an idea in the moment you least expect it, when you wake up in the middle of the night, or during lunch, or even while you are playing soccer. As educators, we should encourage children patiently. And when they really get stuck in their investigation, we can give them some clues which help them to think further. We should also make sure that the challenges we give them are appropriate for their level of understanding. Of course, this method has its limits. We cannot expect that children will discover the whole of mathematics by themselves. For example, I think that not many students would be able to discover the theorem of Pythagoras by themselves. But we can explain them the theorem and then challenge them to find a logical explanation why it has to be like that. Or, in other words, a convincing proof. We are also limited in our time. Therefore, it will always be necessary to teach some topics in a conventional way, just to shorten the process. But I want to encourage you to do mathematical investigations with your children whenever possible, and to investigate together with them. Let's see a small example of what we can discover in a mathematical investigation. Let's investigate some properties of the multiplication table times 9. Now it is good to begin with a rather open question, a question which does not limit us to a single answer or to a single point of interest. For example, we can ask, what interesting properties can you find in the multiples of 9? And let's see where we get with this. When the kids have no more ideas, we can ask some more specific questions to guide them towards some points they overlooked. So I invite you to observe these numbers, pause the video, and try to discover some interesting properties. Okay, did you discover something? Or do you need more time? If you do this for the first time, or if you try to do it very quickly, you may say, I don't see anything. But don't worry, I will show you some of the things that could be seen. And I hope you will be encouraged to discover more things with the projects of this module. For example, I notice that these digits in the tens position are well ordered. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the units digits are also ordered, only that here the order is descending. 9, 8, 7, 6, and so on until 0. This is really a surprising order, and this makes the nines table very easy to learn.
This is easy.
So we ask, where does this order come from? Why is the nines table so orderly? Pause the video for some moments and try to find an explanation. Well, here's an explanation a child might come up with. From one number to the next, we add always 9, but 9 is almost 10. So adding 9 is almost the same as adding 10. Therefore, the tens digits always increase by 1. But to be exact, 9 is 1 less than 10. So when we add 10, then we have to take away a unit. That's why the units always decrease by 1. Adding 9 is the same as adding 10 and taking away a unit. Why? Because 9 is 10 minus 1. I can play and experiment a little with the numbers and discover more things. For example, this. 18 is 20 minus 2. 27 is 30 minus 3. 36 is 40 minus 4. It looks like there is a pattern. Let's try with higher numbers. 72 is 80 minus 8. 81 is 90 minus 9. And actually also at the beginning, 9 is 10 minus 1. Where does this come from? Pause the video again and see if you can explain it. Okay, where does this interesting property come from? It has also to do with the fact that 9 is 10 minus 1. When I multiply a number by 9, this is the same as multiplying it by 10 and then subtracting the number itself. As this works with the number 3, it works in the same way with 4 and with any other number. The mathematical law involved here is the distributive law. With some algebra, we can generalize it and say that this applies for any number n. A teenager could understand this. For children, it is better to stick to numerical examples. Here's another interesting property. In each one of these numbers, the sum of its digits is 9. Now we can ask more questions and expand our field of investigation. When we extend our table beyond 90, what will happen? Will the properties we discovered stay the same, or will they no longer apply? The order of the tens digits is broken here. The 9 is repeated. But maybe we can find an explanation for this. In the units digits, the sequence begins again at 9 and descends, so this seems to be a systematic pattern. This pattern also continues systematically. It must be like this, since we already proved it algebraically for all numbers. As for the sum of digits, 99 seems to be an exception, since here the sum is 18. But after that, the sums are again 9. What do you think is the general rule for this pattern? And how can we prove that it is valid for all multiples of 9? With this, we are already entering into somewhat more advanced territories. Here we will not progress much further without using algebra. But for teenagers, this is a good challenge for investigation. In my program, I had a secondary school student who found an algebraic proof of this rule, almost without help. On that day, she had also brought a friend and said, "He's our class genius. In math, he has always the best grades." After the activity, I had a look at the genius's notebook. He had written down everything I had explained with beautiful handwriting, a perfect notebook. But after that, there was no investigation of his own. Not one original thought, nothing. In that part, he did not know what to do. I thought, this must be the way you achieve the best grades in the school system, by reproducing exactly what the teacher does, without thinking anything by yourself. I prefer that my children get perhaps somewhat lower grades, if only they know how to reason. In the projects of this module, you will have the opportunity to practice several mathematical investigations with your family.